This is Francesco Costantini, and I will present the lab report for Physics 2211 about how to determine the mass of a black hole. Now, in understanding how to determine the mass of a black hole from the movement of the star, which is the data is provided in a CSV file, we'll need to apply Newton's second law of kinematics in this situation as well. However, in this scenario, we will start first from a movement of the star, and then see which forces are acting on the star. So as you can see, that as the force depends on the motion, on the mass of the black hole, we will see. Okay, we can be able to. We need to know the net force that acts on the star. However, we will need to write down the second law of kinematics with the use of momentum, which is the product between mass and velocity. Then we will write the change of momentum in a similar way, which is written as this way. And then we can rewrite the second law of kinematics as the following. And if delta t is really, really low, then the net force can be written as this way, which is the rate of change of momentum with respect to time. Then we will know that we can see that net force can be split up into two components, a parallel component and a perpendicular component of the force. And the parallel component describes the change in magnitude of the net force, whereas the perpendicular component describes the change in direction of the net force. And then, in terms of the rate of change with respect to time, the net force can be written as the following. Then we will presume that only the force of gravity is the only force that acts on the system. This is the code as written, and in order to determine where we will first determine the velocity. Then we will need to determine the momentum, and we multiply both the initial and final velocity with the mass of the star. Then we will determine the change in velocity and the change in time. And then we will determine dp dt as the ratio between the change in momentum by the change in time. And that force will be dp dt. Then to calculate the dp dt parallel, it will be necessary to calculate the product between the rate of change of the magnitude of the momentum with respect to time times p hat, which can be calculated p hat as the ratio between the initial momentum and the magnitude of the same initial momentum, and d mag pd as the difference between the magnitudes of the final and initial momentum divided with time. And then the perpendicular component of the change of momentum with respect to time can be calculated as the difference between dp dt and dt parallel. And then this is run on VIDLE. And the black arrow shows the parallel component of the net force, and the blue arrow shows the perpendicular component of the net force, and the yellow arrow shows the net force overall. And then I will show you how to determine the mass. At first, we will need to determine the radius, and we will presume that the object is moving on circular positions. Therefore, we can freely pick any position as the radius, which is the distance between the black hole and position of the black hole and the position of the star, will always be equal. And this is the value we will obtain for the square of it. Then we plug everything into the equation as net force, which is the value that we calculated through here, and then the mass of the star, which was given us already. This is the change in the radius, the radius which is calculated, which we calculated before, and this is the constant of gravitational motion. And then the mass of the black hole that we obtain is equal to 1.96 times 10 to the 31st kilograms. Now, what does it mean? You may ask. So the net force is the change in time, the change in momentum with respect to time. And the perpendicular component of the net force is the change in is this same value, the change in momentum with respect to time, perpendicular. And the change in net force parallel is the change in momentum with respect to time, parallel. But there's a caveat behind. The values do not represent the same phenomenon. And the forces are what actually cause the change in momentum. And the change in momentum, which is only simply what we can observe. And these relationships can be expressed analytically, but it is misleading to presume that the change in momentum and the change in time with respect to that mass, that the force is just the change in momentum with respect to time. It is the change in momentum is a consequence of the force. And what if we presume that we could find a value for the mass of the new black hole that could be different from the mass that we found from the original one? That would be impossible, because due to Newton's law of gravitational motion, if all terms are the same, then the mass of the black hole cannot change. There's only one value for the mass of the black hole. The only way that it could change would be if you have to change all the other values. So with the use of Newton's second law and Newton's law of gravitational motion, and with the use also of the momentum principle, it is possible to see how an application of how to determine forces from motion, as it was to use it looking at the motion of a star, it was possible to see how the star, how a black hole, how much the black hole's